All right, in this video, we're going to talk about how exactly does a positive charge and a negative charge influence each other when they don't actually touch each other. Michael Faraday came up with an interesting solution to our problem of how exactly these two charges influence each other without touching. What he said is that these charges actually emit an electric field, and that field goes out into space, and that field around the charge is what influences other charges around it. So they don't actually have to touch each other to exert forces on each other. Now, the electric field has a symbol E. Its units are newtons per coulomb. The equation for electric field is the electric force divided by a positive charge. Okay, now we have to have a sign convention for this. Electric field is set up for positive charges, and you'll see how that works in a little bit. If we plug in what our electric force equation is for a point charge, then we get this, and this is only good. Let me remind you, it's only good for a point charge or a spherically symmetrical charge distribution. So kq over r squared has its limitations. The electric field vectors, they point away from positive charges because a positive charge placed out here, remember our sign conventions for positive charge placed out here would be pushed away. So the electric field goes away from a positive charge and it will go toward a negative charge. So the direction of the electric field vectors represents the direction of the force on a positive charge. And the length of these vectors, these arrows down here and over here, tell you how large the electric field is. So the longer they are, the larger the electric field is. And this makes sense because as we get closer to our point charges, the electric field should get larger since it's in the denominator. What's truly important, and you have to make sure that you understand this because this shows up on the test all the time, is we still want to be able to solve problems with forces. So we have to be able to find the electric force from the electric field. And so that's our equation right here. So remember, the electric field times the charge equals the electric force. And we use that in F equals ma and all our regular mechanics type equations. This diagram here is what we call an electric field vector diagram. For an entire grid of points, we draw the electric field vector at that point. Remember, they point away from positives and towards negatives, and the length of them tells us the relative electric field strength. So knowing that, how do we know what the signs of these charges are? Well, if I was to put a little positive out here, it would be pushed away from this one. So therefore, this must be a positive charge. Now, if I put a little positive charge over here, it would be pushed or pulled toward B, so therefore B must be a negative charge. The electric field vectors always point away from positives and toward negatives. How do we know the relative strengths of these two? Now, it looks like A is bigger than B, but that's a little bit of an optical illusion. If we look at point A and count over 1, 2, 3 dots, we get our first arrow. And if we look at B and we count over 1, 2, 3 dots, we get our first arrow, and these two arrows are the same strength. So it looks like A and B are actually the same strength or the same magnitude of charge. The purple vectors represent the forces on Z. So Z must be some particle right here. Notice it gets pushed away from A and toward B. And we know that B is negative and A is positive, so that means Z must be a positive charge. And the net force on this Z positive charge is to the right. Notice how that is parallel to the electric field vectors in that spot. This will always be true. The net force on a charge placed in an electric field will always be either parallel with or parallel against the electric field. Because you only have two choices. It's either a positive charge or a negative charge. So if I place a positive charge right here, it will get pushed up. If I put a negative charge right here, it will get pulled or pushed downward against the electric field. So here's a quick simulation of what the electric field looks like, or a different view of what the electric field looks like around a charged object. Now Faraday said that this electric field radiates outward at a definite speed, and it turns out that speed is the speed of light. So if I just plop this positive charge in from nowhere, you'll see that the electric field radiates outward at a given speed. Now here's our connection to thermal physics from earlier. Everything's made up of atoms, and because everything has a temperature above absolute zero, all the atoms are vibrating, and the atoms are made up of protons and electrons, so they're all vibrating. And so this is what happens. You get these waves that radiate outward. Now this is something like U at a low temperature, but if we get that temperature up higher, then it'll produce higher frequency waves, like the ones that come from the sun. Another view of an electric field, here's a different way to view it, is notice how the electric field radiates outward, and as I move this around, the electric field changes as I move it. And if I put multiple charges out here, I will get a combined electric field picture. And so notice how the electric field will point from positives to negatives. I have two negatives here, so the electric field points into this one or into this one. And if I put a positive charge out here, notice how the force on the positive charge is always parallel to the electric field. Now, this is a positive sensor. If I put a negative sensor out here, like an electron, the force would be in the exact opposite of the electric field. A parallel plate capacitor produces an electric field between the plates, and this is one that you absolutely have to know. Remember, a parallel plate capacitor has a plate on two sides. We charge one up positive, the other becomes negative, and these two charges have the same magnitude. The electric field will always point away from the positive towards the negative plate, and it will be uniform in direction and uniform in strength, all inside of here, until we get near the edges. Now, if we get near the edge out here, it's going to bend outward and become weaker, and it will become weaker and weaker the farther away you get from the center. Let's look at some examples. So we have three particles placed in a uniform electric field as shown in the figure right here. Hey, this must have been produced by a capacitor because there is a uniform electric field, so there must be a positive plate over here on the left and a negative plate here on the right. Which direction will each charge accelerate? Let's do the easy one first. Neutron, neutral, no force, no acceleration. Okay, proton, positive, force to the right in the direction of the electric field, it'll accelerate to the right. Electron, it is negative. Please be careful. They'll always on the test make sure you're paying attention by giving you a negative charge somewhere. So electron is negative, so it will receive a force parallel to the field, but in the opposite direction, to the left. Compare the acceleration of each. Well, neutron has zero acceleration, proton has acceleration to the right, electron to the left, but electron has a smaller mass. All right, so the electric force on the electron is, remember, electric force is EQ. They have the same charge, electron and proton, but the electron has less mass. So F equals ma, electron has a greater acceleration than the proton to the right. Okay, in our next one, we have three charges that are surrounded by an electric field. What is the sign of each charge? Well, let's see. Electric field pointing away, so 1 must be positive. Electric field pointing in for 2 and 3, so they must be negative. Rank the magnitude of the three charges. Well, 2 looks the biggest. 1, 2, 3, 4. Looks like about 5 marks here before we get to the first arrow, where this one looks like 1, 2, only 3, and this one looks like 1, 2, 3, or 1, 2, 3 as well. So it looks like 1 and 3 are the same magnitude, even though it doesn't look that way necessarily because these are pointing inward and these are pointing out. So 2 is definitely the biggest magnitude. 1 and 3 look to be approximately the same. We'd really need a ruler to measure the distance to the first arrow and then measure the size of the first arrow. A proton is placed at X, describe its motion. All right, if we put a proton here, it'll receive a force in the direction of the field, which is to the left. It'll accelerate away. By the way, as it gets farther away, the force on it will get smaller, and so therefore its acceleration will decrease, and so it'll eventually reach a top speed. The electron is placed at y, and an electron will get a force in the opposite direction of the electric field. So y will accelerate to the right, away from the negative charge. Hey, that makes sense because this is negative and y is negative, so they should repel. So it should make sense. All right, here's number 8. Two charged particles are attached to an insulating ruler so they cannot move as shown in the figure. So here must be our ruler. It's marked off in centimeters. We have a +2 microcoulomb and a -8 microcoulomb. Please be careful of your units. What's the direction of the electric field at 2 centimeters? That's right here, halfway between the two charges. I'm going to need to work this one out on paper. All right, to help us understand this one better, I'm going to color code mine. I'm going to make the 2 microcoulombs pink, and I'm going to make the -8 microcoulombs blue. We're looking at a spot here in the middle. So the electric field should be toward the blue one and away from the pink one. Now I've drawn the pink one smaller because it's a smaller charge, but they're both working together. So the answer to part A is to the right. Our electric field will be to the right. Okay, is there a location on the ruler where the electric field equals 0? If so, calculate where it is. If not, explain why it does not exist. Okay, well, it can't exist in here. That won't work. So I have an electric field that points away to the right here and away to the right here from our positive pink charge. And it points inward to the left for the blue one and inward to the right on the blue one. I draw the blue one bigger over here. It's a bigger charge and we're closer. So this won't work either because the blue electric field will be bigger than the pink electric field over here on the right. Now here we have a possibility. We're farther from the blue one and we're closer to the pink one. So let's see how this works out. Remember that the electric field from the blue and the pink must be equal, and that's KQ over R squared must equal KQ over R squared. I'm going to call this Q1 and 2. So there's my number 1 and 2. The K's cancel out because they're equal. I'm going to try and relate these two. This one is a 2 microcoulomb, that's an 8 microcoulomb. So if I put 2 microcoulombs here over R squared equals 8 microcoulombs over R squared here, and this is R1 and R2, then notice that this is a 1:8 or a 1:4 ratio. So I end up with a 1 over R1 squared equals a 4 over an R2 squared. And so that means R2 squared has to equal 4 R1 squared. Square root both sides, what I end up with is R squared is equal to 2 R1. Now, I mean, R2 is equal to twice R1. That means we have to be twice as far away. So let's see, that's 1, 2, 3, 4. So 1, 2, 3, 4. If we place, or if we look at this spot right here, that's a distance of 4, that's a distance of 8. So this is the location right here where the electric field would equal 0. Our next problem says points A, B, and C are located in the center of square arrangements of charges as shown. What's the direction of the electric field at each point A, B, and C, and rank the magnitude of the electric fields at these points. See if you can do this on your own, and then we'll work it out together. All right, I'm going to color code this one to help us out as well. So I'm going to make this my orange charge right here, and so it's positive. It has an orange electric field that's away. This is positive, orange electric field away. This is positive, orange electric field away. And then this will be my pink charge right here. That's negative. It's going to be toward itself. Negative, toward itself. Positive, careful, away from itself. And then here's a blue charge down here. It's positive, so that's away. Negative, so it's toward. Negative, so it's toward. And then I'll make this my green charge here. Negative, so it's toward. Positive, so it's away, and positive, so it's away. So now look what we end up with. these are all the same magnitude, so they're going to cancel. So our electric field over here is 0. And right here, these are all the same magnitude. So I end up with 2 of these this way and 2 this way, which will add up to be an electric field to the right. Now, if this is 2E, if I call each one of these little ones E, then I get 2E here, and this is a little square, so this would be a 45, 45, 90 triangle. So that would be 2 times the square root of 2E. This one right here, those cancel, so if that adds up together, that's 2E. So this one is the biggest electric field. This one is the next. This one is 0. This one points to the right. This one points down and to the right. Now, electric fields produce electric forces, and forces are related to mechanics. So here's an example of a mechanics problem that involves electric forces. So we have an object, this sphere, M, that's suspended in an electric field. Can you tell where the capacitor plates are? There's a positive plate over here on the left and a negative plate over here on the right. Now, it's suspended there and not moving. The question is first of all, what's the sign of this charge? And the second thing is can you derive an expression for what the magnitude of that charge is? See if you can do it, and then we'll work it together. All right, first off, what's the charge on the sphere? Well, we can see that this sphere would normally hang straight down, but it's being pushed to the right because the thread is tilted to the right. So there has to be a force this way. It's an electric force. The electric field is to the right, force is in the same direction, so that means the sphere must be positive. Okay, now derive an expression for the charge. Well, this is a statics force problem. So there's a gravity force down, mg, there's an electric force this way, and there is a tension force up and to the left. Let's break this down. There's my theta, so this must be t sine theta, and this must be t cosine theta. So in the x direction, we have that the electric force equals t sine theta. In the y direction, we have that t cosine theta must equal mg. I don't see charge anywhere here, or do I? So here we are, the electric charge shows up right here, and remember, this is not k, q1, q2 over r squared, okay? We don't have a spherical electric field going on here. We don't have two charges. We just have an electric field, right? So this is going to be electric field times the charge, EQ. Okay, drive that into your brain. EQ for electric force. All the time, every time, whenever you can use it. Now, if you have 2-point charges, well, then you can use K, Q1, Q2 over R squared. T sine theta, I'm going to solve this for T. That's mg over cosine theta. Take that, plug it in, and I get EQ equals mg, that's a tangent theta, and so my charge will be mg tangent theta over E, and let's make sure that's correct and that it's all of the things that are given. Let's see, E is given, check, theta is given, check, M is given, check, and G is a constant, so we are good to go. Here's another example of mechanics with electric forces. So you can have a force on a moving charge. So here we have two capacitor plates, so our electric field will be directly to the right, away from the positive plate, toward the negative plate. If we shoot a proton in through this uniform electric field, it will receive a uniform force to the right. This is just like throwing a baseball in Earth's gravitational field. Instead of getting a force to the right, we're going to get a force straight down on a baseball, and so it will arc downward in a parabolic arc in two-dimensional motion. Same thing happens for this proton. It's going to go through a parabolic arc, but this time the parabola is to the right. Here's one last example of electric forces and mechanics and how they tie together. So first off, let me explain what a dipole is. Right here we have a dipole. A dipole is an object that has no net charge. It's neutral, but it's polarized. So one side's positive and one side's negative. If we put this in an electric field, then once again, where is our capacitor plates? We have a positive plate up here and a negative plate down here to produce this uniform downward electric field. If I put this dipole in this uniform field, the negative end will receive a force in the opposite direction of the electric field, and the positive end will receive a force in the direction of the electric field. So it's going to rotate. It's going to receive a torque, in this case, clockwise, and it will rotate. This one over here will rotate in the opposite direction, counterclockwise. This one right here won't rotate at all because the negative force on the negative charge is directly up and the force on the positive charge is directly down. So if you put these things in an electric field and they're not already aligned, they will try to align with the field. And if there's no friction, they'll oscillate as they try to align and eventually align with the field. One last important thing to note, since this dipole does not have a net charge, it will not translate in the electric field. So like, take a look at this one right here. It's the easiest one to see. These two forces will cancel. And so while it may try to rotate, it will not try to propagate or translate in the field. All right, that's it for electric field. Our next video will be electric potential energy and electric potential. Until then, see ya.